So, as I've mentioned, a derivative measures a rate of change, but it's not just in curve sketching we experience rates of change. Any time there is a rate of change, the problem lends itself to using calculus. So, all right, we've got a block of ice in the form of a cube, 10 centimetres long. It's melting so that its dimensions will decrease at a rate of 1 millimetre per second. So imagine you got your ice block and it's going down 1 millimetre per second. What we're interested to know is once it gets to 5 centimetres long, so half of the edge is melted away, what rate is the actual volume decreasing? Okay. So there's my little block of ice there. I'm just going to call the edge length x. Now, I want to know how volume is changing as time changes. So there's my rate, dv dt. How does volume change with respect to time? And I want to come up with a formula for this. They've told me how the edge changes with respect to time. So I know dx dt is negative because it's decreasing, and 1/10, because what do they say? 1 millimetre is, of course, 1/10 of a centimetre. So I want dv dt. I've got dx dt. So using the idea of the chain rule, we know volume is x cubed. I can create another rate, dv dx. dv dx would be 3x squared. So now I can combine this into a formula because dv dt would be dv dx times dx dt. So subbing in what we know, 3x squared for dv dx, dx dt was minus 1/10. I come up with a formula for the rate of change of volume with respect to time. I just need to substitute in the length of the edge of the ice cube to come up with the answer. Well, they want us to know when 5 centimetres long. So if I sub in x equals 5, we get our answer of minus 7.5. So I now know that the volume will be decreasing and the units would be centimetres cubed per second in this one. A vessel, right? An inverted cone, vertical angle 90 degrees. Depth of the water of the vessel is x centimetres. Let's draw a little diagram there. So that's what we're basically talking about, an upside down cone which is containing some water. The vertical angle, it's a right angle down here if we were to take a cross section. What is that actual volume of water? Well, volume of a cone is, of course, no, 1/3 pi r squared h. Remember, a pyramid is always 1/3 of the corresponding prism. So when we talk about a cone, it must be 1/3 of the cylinder. So 1/3 pi r squared h. Now what do we know? We know the depth of the water is x. Now, it would be nice to know the radius because then I could work out the volume of the cone. X is obviously the height. But we know that that's got to be 45 degrees because our cone is going to be symmetric. So that's 90 degrees at the bottom, must be 45 either side. Well, if I've got a right angle triangle with 45 degrees, that's an isosceles triangle. So I know the radius must be x as well. So the volume of water then, 1/3 pi r squared h, but the radius is x, so is the height. So we get 1/3 pi x cubed. So I have a formula for the volume in terms of x, in terms of the depth of the water. All right, so we're going to pour water in at a rate of 0.2 centimetres cubed per minute. We want to find the rate that the depth is increasing once we get to 4 centimetres. So what are we trying to find? We're trying to find dx dt. What do we know? We know dv dt. They've told us we're pouring in 0.2, which is 1/5. So I want dx dt, I've got dv dt, so ideally now I want something that links volume and displacement together so I can create dv dx. Which was the point of the first question. There's the formula. It links velocity and displacement together. So v is 1/3 pi x cubed, we just found. So dv dx is pi x squared. So subbing that in now, we can use our chain rule. Dx dt would be dx dv multiplied by dv dt. So dx dv, well, dv dx is pi x squared. Turn it upside down, we'll get dx dv. So that's 1 on pi x squared. Dv dt, we were told, were 1/5. So there's our formula, 1 on 5 pi x squared. So the situation we're looking for, where's the info? There it is when the depth is 4 centimetres. So we want to know when x is 4, and as an exact value, it's 1 on 80 pi. And the units on that one would be centimetres per minute. Centimetres per minute. Okay. All right. Well, let's have a go at just a handful out of 7H. This idea of solving practical problems using our calculus.